Hello, for today's video lecture we're going to be talking about work, kinetic energy, and potential energy. So far, we've used kinematics to relate position, velocity, and acceleration, and we've used the force, mass, and acceleration branch of kinetics to relate forces to those accelerations. So we're now going to move into a section where we discuss the work and energy methods, and this is another branch of kinetics. So this is an alternative to the force, mass, and acceleration method, relating those forces to the motion of the body. So the work and energy method is best summarized as this. The work done to a system will be equal to the change in that system's energy. If we put that in equation form, we often will write this as W equals delta KE plus delta PE. W is the work, and then delta KE and delta PE are two different forms of energy. That's kinetic energy and potential energy. We'll talk more about why we split that up later. So before we go into detail on solving these problems though, we're going to need to understand and fully define what work is, what kinetic energy is, and what potential energy is. So work at its most basic level is a force exerted over a distance, and this is not instantaneous. So we have to exert this over a distance, so it happens over a period in time. Kinetic energy, this is the energy that a body possesses by virtue of being in motion, and this is defined at an instant in time. So usually we're going to have in our equation that delta KE and delta PE is final minus initial, and then the work happens in that time between the two pieces. Finally, we have potential energy, and this is energy stored up in an object that is lifted up high, that's gravitational potential energy, or energy stored up in a spring, that's going to be our elastic potential energy. There are other forms of potential energy and potential energy that we could encounter, but we're not going to discuss that in this course. So that's going to become potential for expansion in the future. And again, these energies are defined at an instant in time. So potential energy happens at one instant in time, and we're going to do final minus initial for our delta KE and delta PE values. All right, going into a little more detail. So work, the work done to a system at its simplest form will be a force times a distance. So say we've got some box sitting on a surface, and I push that box with a pushing force with magnitude F push, and it moves some distance d. So the work done by that force would be the magnitude of the force times the distance traveled. If we have a force that opposes motion, so in this case we've got our friction force on the base, so this is going to cause negative work. So the friction force is going to the left, my distance traveled, or my displacement in this case, is going to the right, so I'm going to have negative friction force times distance, and so I'm going to wind up with a negative work done by this force. So if I am helping motion, it's positive. I am opposing motion, it's negative for my work value. And the parts that are neither opposing or helping, in this case, imagine we've got a pushing force, but I don't push perfectly horizontal, I kind of push down. Only the component of the force in the direction of motion does work on the system. So in this case, my distance traveled, that's horizontal, and so only the horizontal component of the pushing force, or F push cosine theta, times the distance is going to be in the work for my system. If I do wind up with any forces that are perpendicular to that distance traveled, in this case F normal would be perpendicular to my distance, with no horizontal component, I have no work done by that normal force. So keep this in consideration when looking at the work on a system. All right, so also sometimes we're going to encounter a force that changes as the body moves. So if the force is not a constant value, then we need to bring calculus into the equation. So if I've got my force function, so f of x, I can kind of plot it out from some starting point to some final point. The work done by the force will be the integral of the force function over the distance traveled. So going from some minimum x value to some maximum x value, I simply integrate f of x and the area under that curve would be the work done. All right, next, moving on to kinetic energy. So kinetic energy of a body, or of a particle in this case, will be as follows. So Ke equals 1/2 mv squared. M is the mass of the object, and then v is the speed of the object. So v usually is velocity, but in this case I only care about the magnitude of the velocity, which itself is just the speed. So in our conservation of energy equation, we're going to use change in kinetic energy. So we always had delta, or we have delta Ke in our equation. So assuming constant mass, it's just 1/2 mv final squared minus 1/2 mv initial squared. So final minus initial for our kinetic energy. So while the direction of the force was important for work, here the direction of velocity is not going to be important. So kinetic energy, and for that matter potential energy, are scalar values. They don't have a direction, they can't be broken down into components, so we don't have horizontal and vertical kinetic energy, we just have kinetic energy. And they cannot be negative, although changes can be negative. So I can have zero kinetic energy, I can have positive kinetic energy, but I can't have negative kinetic energy. That delta Ke value, though, final minus initial, that can be negative in my equations. All right, next, moving on to potential energy. So it has many forms, but in this course we're going to focus on gravitational and elastic. So our gravitational potential energy, delta PE, is going to be mg delta H. We'll go more detail into this. G is the acceleration due to gravity, so this is our 9.81 meters per second squared, or 32.2 feet per second squared, depending on what units we're using. And then delta H is the change in height of the object. If I move upwards vertically, that is a positive number. If I move downwards vertically, that is a negative number. And our elastic potential energy, our delta PE for that, this looks similar to what we had with our kinetic energy. So 1/2 kx final squared minus 1/2 kx initial squared. K represents the spring constant, that's the stiffness of the spring, while x represents the difference in length from the resting length. So if the spring is naturally 5 inches long, x will be 1 inch if I compress it down to 4 inches, or if I stretch it out to 6 inches. It's the difference from kind of the natural length of the spring. All right, so going into more detail with both of these pieces. So gravitational potential energy is not really an energy at all, but instead represents the work gravity will do to a body as it moves. So if I've got some box, I imagine I've got gravity pulling down on it, and I'm going to move this box upwards. The work done by that gravity force, first of all, it's going to be negative because as I move up, gravity is pushing down, so it's a negative amount of work there. The magnitude of the force is mg, and the distance traveled is our delta h. So force times distance, mg times delta h. So assuming we're lifting the object upward, this quantity is negative, like I said, because the weight force is always opposing the upwards motion. So rather than treating this quantity as work, though, we're going to move it over to the energy side of the equation. So as we move it from the work to the energy side, algebraically, as I move something from one side of an equation to the other, it's going to change the sign. So the negative sign that I had in my work is going to turn into a positive sign. So for delta PE, when I move it over, it's just mg delta h. There's no negative sign left in the delta PE part of this. And again, m is mass, g is the acceleration due to gravity, and delta h is the change in vertical height of the object. So if we move it on a slant, only account for the vertical part, upwards is positive, downwards is negative. Finally, we're going to talk about linear springs and elastic potential energy. So imagine we have a spring attached to a mass, and we compress that spring going from point A to point B. So here's our spring. I started at point A over here. This is unstretched, and I've compressed the spring down to point B over here. So the magnitude of the force on the box is going to be equal to K times X at each point along its path. So K is the stiffness of the spring. K is larger for stiffer springs. It is smaller for kind of stretchier springs. And x is the distance that we've stretched from the resting position. So if I've gone from point A over here to point B, I've say I've traveled 4 inches, my x value is just going to be that 4 inches. The direction is not going to be important. Whatever the direction is, the spring is going to oppose that, basically. All right, so the magnitude of the force changes as we move the spring. So the larger x is, the larger that the force is. So because of this, this is a non-constant force, and so if I look at the work, I have to integrate this. So if I integrate from 0, that's my unstretched length, to whatever x is, my force is negative kx because it is opposing that motion, kind of like gravity. If I push it one way, this one's going to be pushing back. And so if I integrate that function, I get negative kx squared, in this case, as my work done by the spring. So like with gravitational potential energy, elastic potential energy doesn't represent the energy at all. This represents the potential of a spring to do work. So as I move it from the work side of the equation over to the energy side, I get rid of that negative sign. So the potential energy of a spring is usually just defined as 1/2 kx squared. Again, k is the stiffness of the spring, and x is the amount of stretch that I've put in the spring. So I could either stretch it out or compress the spring. Either way, I count that as x being a positive value. All right, so when examining the change in elastic potential energy, so delta PE, we're simply going to take the final minus initial potential energy. So delta PE equals 1/2 kx final squared minus 1/2 kx initial squared. One element of caution I would put in this place is you cannot do delta x. So 1/2 times k times delta x squared is not going to be algebraically the same thing as what we have up here. You always have to, because of this squared value, you always have to include x final and x initial, not just delta x in your equations. Finally, one note with both gravity and spring forces, these are conservative forces. So what does that mean? It means that the exact path taken is not important, just the change in height, delta h, or the spring length values x for the springs. This is easiest to illustrate with like a pendulum. So if I've got some ball and I let it drop straight down, this is my delta h over here. The work done by the gravity force in this case is going to be the same as the work done by gravity on a pendulum. So even if it swings down, so if my delta h is the same, this is going to be the same amount of work. You say, well, the distance is longer in this case. Yes, but remember the gravity force is not entirely in the same direction as the distance or the displacement in this case. So the component that is in this direction is going to be smaller. So in the end, it works out that it is path independent, which means that it's only the change in height for this case. And it is only, for springs, it's only the x value at that instant in time. So it can kind of go oscillate back and forth a couple times, but I can still make this work, even if it's not kind of a direct path one to the other. So this is actually the strength of potential energies, is this path independence. So keep that in mind as we go into other work in the future. All right, so that's all we've got for today's video lecture. Thank you for watching, and I hope to see you again.